Hi, welcome to this program on electrified vehicle electrical anomalies. What is an anomaly? We've done these before. It's something that deviates from what is standard, normal, or expected. So this series of electrified anomalies, we're going to do two of them today, is on the electrified vehicle. So this is for plug-in hybrids, electric vehicles, you name it. They all can fall into these kind of anomalies. So we're going to give you, the professional technician, some technical explanations to what's going on, what causes these anomalies, and are there anything to be concerned about as you work on hybrids, plug-in hybrids, and electric vehicles. Not all strange electrical conditions, keep in mind, are a sign of a vehicle problem. Some conditions are actually normal. We'll show you some today. And those conditions I'm calling an electrical anomaly, kind of a quirky thing. After reviewing this program, you'll be able to identify at least two of these anomalies and determine if there's a problem or there's, no concern. It's just a normal thing or abnormal, an anomaly. All right, let's get started here. Item number one, electrified vehicle. So we're going to use a Prius today with the generation 3, so it's 200 and some volts of DC. And we're going to look at high voltage isolation circuits, and we're going to look at them on several different places, and we'll start out with the DC bus. So what is a high voltage isolation circuit? It's basically how the vehicle's electronics detect if there's some issue with the orange cables, the high voltage circuits. Maybe a lift arm has compromised a cable, and it's not a dead short, but it's just starting to leak. And it can include air conditioning compressors, even with the oil used in the vehicle's AC system. Might not cause a dead short or a shock to somebody, but could cause a little breakdown in the resistance of that refrigerant. So we'll talk about, in this case, the high voltage battery pack, both at the inverter side, and we'll go back to the back with just a good used, actually kind of ran down, used high voltage battery pack up on the display. So leakage detection, when you set those codes that says there's insufficient insulation or resistance between chassis ground and the high voltage, that's what we're looking for. All right, so basically what it is, it kind of acts like a high-tech version of a GFI, ground fault interrupter. You've all seen them. They're in your shops. They're in kitchens and bathrooms. They're required by electrical code in certain situations. And basically it looks to see, without any solid-state components or anything weird, weird high-tech, it basically looks to see if there's between 4 to 6 milliamps of leakage between the hot wire, that'd be the black wire in a wall connector, and neutral or earth ground. So hybrid electric vehicles have a high-tech version of that, and it's called isolation fault detection, or an isolation circuit. Let's take a look and see what it looks like on the vehicle. So when you look at the schematic, and this is from Toyota, this is the service main relays. Nothing new. You probably, if you've worked on these, you're an advanced hybrid tech, you've seen this all the time. There's a service plug on the left, completes half the battery with the other half the battery in series together. You got 3 service main relays, SMRs they call them. Sometimes they're called contactors. You got one that turns on. It's got this pre-charge resistor to help charge the capacitors in the inverter so that we turn it on nice and easy. You've got a contactor or a relay, service main relay, for the positive circuit, high voltage battery, and for the negative. So you see on the bottom is the negative, and looks like on the top, SMR2 is the positive. What we're going to do is draw another circuit within this simplified block diagram. We're going to draw an isolation fault circuit. So this is kind of what it looks like. It's some more resistors, but this time these resistors are super high ohmage. So now we've added some additional circuits that aren't in the factory Toyota diagram to kind of make it easier to see. Actually, Toyota has some of these circuits in some of their training diagrams, but in this case, I've really simplified it so you can see kind of what goes on. So you see that it says V for victory. It's actually V for voltmeter, not a real voltmeter, but the logic chip looking at the voltage of what we're doing by bleeding off deliberately a tiny bit of current between each of the buses, the positive high voltage bus and the negative high voltage bus. We don't use a common chassis ground like a 12 volt system, or even some of the mild hybrids these days. 48 and 42 volts are using a common chassis ground. Not so with the orange cables. With the higher voltage vehicles, it is a safety priority and requirement legally that they have to have a floating negative or isolated negative high voltage line, and the same thing for the other orange cable for the positive. So you see we tie a couple high ohmage resistors, and it has to do with the requirements for how many ohms per volt we have of isolation resistance. So in this case, we have 300 volts approximately on a particular vehicle, not this Prius, it'd be a little bit less. Let's say we had a Ford, an older Ford Escape at 300 or 330 volts. If we did 150,000 ohms of resistance between either of those 300 volt cables and chassis ground, we'd have 2 milliamps of current flow. Now, if you think about that, that's still enough that you would feel it, and it could possibly be injurious. It doesn't take many milliamps at high voltage to cause you problems. So you still don't want to ever touch any high voltage connection without proper personal protective equipment. So class 0, 1000 volt gloves, tested and inspected every time you use them, and tested every 6 months by professional service. So when we see 2 milliamps, doesn't sound like a lot, but it is enough. You could probably feel it at the very least. And if there's a problem, it could be worse. So we're going to look at that high voltage bleed off on a vehicle that's working correctly. But we're going to have to do some things intrusive that I do not recommend you doing unless you are doing this as an educational project like I'm doing, and making sure that nobody watching, that would be you folks on this video, are going to just run out and do this without proper instruction. We're going to be safe with gloves, and we're going to, even though it's kind of cumbersome to work on them, we're not going to be probing around underneath this Generation 3 Prius inverter cover, which has been removed, but we're going to make it so we have the high voltage system comes to life. We're going to bypass the next topic of our circuit anomaly, or electrical anomaly for electrified vehicles, which is HVILs, high voltage interlock circuits. We're going to bypass the high voltage interlock circuit real quick and show you what the voltage leakage we're talking about, the high voltage isolation circuit. So it looks kind of like that if we just do a generalization, simplification. If you have too much voltage dropped on either side, the positive or negative, you'll have a code such as a P0AA6, which is hybrid battery voltage system isolation fault. That's what they're called, isolation faults. So let's go ahead and take a look at another vehicle, a Ford Fusion hybrid, that I did the same test on. I'm getting ready to do here on this Prius. And you can see where I'm probed. I'm actually going between chassis ground with a black lead and probed right into, I removed a cover so I could probe, not pierce, but just back probe a crimped high voltage connector. It does the same thing on the positive side, it does on the negative side. Watch that voltage. It goes down, it goes up. I've got the leads reversed, but it would be about up to 200 and some volts, and then it goes back down. So I think this is a 260 some volt vehicle if you measured between the negative and the positive. But in this case, I'm going between chassis ground. I'm checking out that isolation fault detection. That's a couple of milliamps just as a test circuit. And it is moving back and forth. This will make sense when we look at its Stellantis schematic, because they're doing things a little differently, and that's a high voltage electrified vehicle anomaly, all right? So let's go ahead and go into the hands-on on this Prius and look at those voltages. So first thing I'm going to do is I'm going to check the dash and make sure the dash is dark. I don't have any lights on. Now, if I was doing a power down, I'd take the 12-volt battery so it couldn't have the dash come to life, and I'd remove this plug and so forth. But I'm actually going to have a live circuit today, like I said, only for the folks that are in the education process, to show you, the technician or a fellow educator, that how this can be done. It is not a normal service procedure. It is a demonstration procedure, okay? So I'm going to get the gloves on, and I'm going to put in place the high voltage HVIL, high voltage interlock circuit, which comes off when you put or you remove this service cover. So now I'm going to pull this off. Sometimes I got to pry on it. I may have to do that yet. I want to make sure I don't lose it. So I've done it a few times, and hopefully I don't lose it today. So I pull it off the cover. I just kind of study which way it goes, and I put it down in the hole like this. Okay. And I may need some assistance of something, the next best thing to a pair of insulated pliers. I will use these long gator clips to kind of help me guide that down in there. And it's down. Okay. So once that is in the hole, as if this cover was safely in place to prevent any kind of injury. So basically I'm circumventing the safety here for a test demonstration. Next thing I'm going to do is I'm going to get my meter ready, and I want to use as unintrusive leads as possible. So I'm going to take, on the black lead, we don't care so much about that because that's going to be going to chassis ground. But before I do that, I'm going to go ahead and show you the voltage across the two orange cables. So to do that with some degree of safety, I don't like probing down into a live inverter. And I may need to take these back off for a minute. These are category 3, 1000 volt meter leads and tips. I want as little exposed as possible. Get the gloves back on. See if I can get a ready light here. Push my foot on the brake, and I have a ready light. Whether it's running or not is irrelevant. That's the nature of a hybrid. So now I'm going to turn on. Now, in a real condition where I'm doing a service procedure, I want this thing dead. I want it powered down, de-energized, and I would have that cover on there, all right? But in this case, the cover is removed, and I have put the high voltage interlock circuit down in the connector, so it does not protect. That's why I'm being very careful here with extra insulation on my probes and, of course, the high voltage gloves. And I got to get my meter out of manual ranging here. Put it into auto range. There we go. Because I know this particular meter will fool me and say there's no voltage there. So it's very important you have a voltage proving unit, high voltage proving unit, and a way to do a live, dead, live test very accurately. But we're going to be measuring live. Obviously, it wouldn't be running if it wasn't live. So I'm going to pick 2 of these orange cables that terminate with these 10 millimeter nuts. And I believe this is positive and this is negative. Sure enough, I'm seeing full system voltage, 238.9 volts if we're charging this high voltage battery pack in the back of this Prius. Not the one on display, but the one down in the hole. So, engine's still running. It will be shutting down any moment now. Now let's do another test. So that will be checking to see if you have contactors or subsystem main relays working. That would be a standard test, although they don't tell you to do it that way. You'd probably do it at the battery pack, but underneath here, I mean, obviously when you pull the inverter cover off, the H-fill shorting bar comes with it. But we have put it back in the hole to do a more intrusive test for advanced technicians that know your safety. Again, don't try this unless you are, I would recommend you be an ASE L3 and have both of your safety certifications from the ASE's XEV under your belt. But you wouldn't even want to wouldn't even think about having a vocational student do this or a new technician. So what we're going to do next is we're going to still keep that meter right there. We're going to take one of the protective tips off. I can do that with the gloves on, I think. I'm going to put a gator clip on here, like that. I'm just going to go to any chassis ground. I mean, the inverter cover will be fine. It's a decent ground. Get a good grip on it there. Yeah, maybe this little pin will be okay. There we go. Got on a good ground. If we wanted to check a ground, we could go to something that's DC voltage. But let's see what we're getting here. I didn't power it down. I didn't de-energize it, didn't even turn the power button off. I've got it set for DC auto ranging. I'm gonna go back over here to the positive 10 millimeter screw that holds that positive orange cable on there, and I'm seeing voltage. Now I shouldn't see voltage between chassis ground and the positive, and I'm at 125 volts and fluctuating. I've noticed they all do that. And I go over to the negative high voltage, and I see a negative sign, and it's also 123. So going back and forth between the two. Oh wait a minute, this is actually a little lower. So 92, 95, it's fluctuating. 130, fluctuating. What we're having here is an anomaly. This is normal. This is what I've seen. Now, I have seen those voltages a little closer to each other. But what we're seeing is we're seeing half of the high voltage battery voltage dropped across at high ohmage, therefore current limiting to a milliamp or two of deliberate bleed circuit, and that is how the computer determines, hey, wait, I'm not just seeing 1 or 2 milliamps, I'm seeing 5 or 6 or 10. So if you look at those charts on high voltage and milliamps, 15, 20, up to 50 milliamps, doesn't sound like a lot. There's where you get into cardio problems and pulmonary problems, in other words, your heart quits beating and you quit breathing, you can't breathe, and things like you can't let go, and your flesh is burning from the inside out. So electrical burns, electrical shock, and all the associated traumatic bodily injury things that can kill you are nothing to joke about. You have to take them very seriously. So if the computer sees more than that specified tiny, minute amount of milliamps and that particular voltage. In fact, the voltage is different for different models. What it sees between chassis ground and the positive high voltage, chassis ground and the negative high voltage, those numbers can help you when you try to figure out which is the problem, the negative or the positive, and then get your insulation tester, your mega ohm meter out and start doing the testing. So it's very interesting. A lot of specs are out there if you follow particular flow charts for code related to high voltage insulation leakage. Okay, so I'm back at the back of this demonstration Prius. Now the battery pack that was running the show that we've seen from the front of the vehicle in the engine compartment, the actual working battery, that's obviously got, the CAN bus and the high voltage and the low voltage wires going to it for the car. It's a functional car. This is just a demonstrator battery. So this would be like you might have in your shop in the back room, hopefully secured properly, labeled, marked, controlled access, all that stuff. But if you are in the business of, you're a recycler, or you get a battery, a good used battery, or just a demonstration battery for educational purposes from a recycler, beware that just because they say the voltage is pretty much, it's ran down. I see a bunch of corrosion on these battery module connections, a typical old battery, okay? If somebody puts an orange plug in, even if they don't, there is potential. This is like a box of rattlesnakes. Any high voltage battery, nickel metal hydride, lithium ion, doesn't matter. If it's high voltage battery pack designed for electrification, for anything above 50 volts especially, and that's all the orange cable vehicles, hybrids, plug-in hybrids, and EVs certainly, any battery pack is potentially like a box of rattlesnakes. And if you take the cover off that box of rattlesnakes like we have here, you have a lot of safety issues potentially that could occur. Let me demonstrate. So this battery, I'm going to put in a service plug, okay? I don't even have to even pop down the H-fill. I'm just going to leave it up. So I've got it in place. We have now the 125 amp fuse that is connecting part of this side of the battery pack to the other side, and whatever we got is what we got. And if I go between the two cables that would go to the service main relays, and now I see 62 volts, certainly enough. It's above 50 volts, or it's above 60 volts for the standards for DC potential injury or worse, all right? So that's an OSHA thing. Actually, they say 50 volts, AC or DC, doesn't matter. I'm seeing 63 volts between the positive and the negative orange cables that would go to these service main relays. They're going to be off right now, but so that means if there was any orange cables from this point forward to the vehicle, it should, have no voltage going forward. But in the battery pack, back to the snake analogy, it's a box of rattlesnakes with the lid off, okay? Now let's see if there's a high voltage interlock without any 12 volt, any bean, can, whatever bus that this Toyota might use. This is just like basically laying on a workbench at your shop or your school, okay? So I'm gonna go between one of those orange cables and chassis ground and see if we get that deliberate bleed, and we do. It's about 15 volts. And just for grins, let's go ahead and go this old worn out battery with corrosion, just used for teaching. And we'll go to the other orange cable, and it's got 29 volts. So this is going to be low current through those high ohmage isolation bus circuits, high voltage insulation or isolation circuits. We're seeing it in action. This is a passive circuit. Obviously, we don't have 12 volts and some electronic module to turn on and apply those high ohmage resistances. We are seeing them now on a static battery pack, just sitting here like in a mock workbench type of situations. So to summarize, with this particular battery pack, whether it comes into your shop from a recycling yard as maybe a project for you to work on, or it comes into your school for demonstration purposes, whatever the case may be, treat it as if you don't know the condition. If it's a particularly old rundown looking pack like this with a lot of corrosion on it, and somebody says, oh, there's no voltage on that, don't believe it. Treat it like the box of rattlesnakes. I'll call it reptiles or razor blades. It doesn't really matter. A box with the lid off of either in it, if there's potential for injury, you want to consider it as if they're biting or they're cutting, one or the other, because that's exactly what happens if we were to get a hold of 60 volts even. So at the very least, you're going to make sure you remove the service plug, but that only drops a battery into half. So if it was like 70 or 80 volts, now at 35 or 40. What if it was 100 volts? That's still pretty worn down, run down. Now we have 50 volts, certainly enough to cause injury. So not only would you want to lock up the service plug, we'll do a lockout that way. You want to do a tag out. You want to make sure that the room this is in is secured, that the cabinet or whatever it's stored in within a room is secured and properly marked, danger, high voltage. So the documents for the XEV level 1 for electrical wear person or level 2 for electric vehicle or hybrid technician, those documents are free to download from the ASE website. So be sure you do that. You'll get a lot of helpful information regarding things like signage and lockouts, tagouts, and proper storage of battery packs. Well, we talked about the anomaly of the voltage isolation, high voltage isolation circuits. Let's talk about the last topic that I mentioned was HVIL, high voltage interlock circuit. That's it's our second electrified vehicle anomaly. Now, it's not much really strange about them. They've been around for years, since the very first hybrids, and they're still on vehicles, even with the battery electric vehicles today. Let me show you where these high voltage interlock HVIL circuits are, right here. You see the little tiny wires and that white plug I'm pointing to? That's an HVIL. You're like, well, that's not high voltage, that's not an orange cable. Well, it's a watchdog circuit for the high voltage orange cables, or in this case, for the plug. So when this plug, service plug, goes in, and I latch it like that, then I'm putting the high voltage together in series, but then when I go from extended to snapped in place, a little compression of the plug, the shorting bar right here in the end of this orange service plug, or grip plug as Toyota calls it, is now engaged into the circuit that leads to the other end right here, the HVIL. So let's go forward to the front of the car with the meter and see what the HVIL looks like in other places, because when you disconnect something, remove a cover, the same low voltage circuit that's a watchdog for the high voltage system is going to be in place, and we'll actually see it live on the vehicle with a voltmeter. So let's do that now. Now on my way up to the front of the car, I'm going to do one thing, and we'll be very careful. I'm not going to put my foot in the brake. I'm simply going to hit the power button twice. First press of a smart key car like this Toyota is accessory. You know, where you can listen to the radio, maybe run the wipers. And the second press of the power button without the foot on the brake would be the key on engine stop. Now, if I put my foot in the brake at any point in time and hit the power button, I would have a ready mode. And the engine may or may not start, and if there's an issue, it might have a triangle for a master hybrid warning indicator and tell you got a problem, or it may not even say ready if there's an issue. Let's just go ahead and reach in. In fact, I'm going to open the door and do it. I'm going to press it once. There's accessory. It looks like the radio might light up. And then a second time, I do not have anything that says ready. Okay? So that means, you can't take it for granted, that means it shouldn't have high voltage up here. But I'm still going to wear the gloves for what I'm going to get ready to do next. I'm going to remove the high voltage interlock circuit. So the H-fill connector up here, there's one on the service plug, a shorting bar, connects into the service plug harness, and a small little white plug with the little tiny wires in them. Let's just see what the voltage is, because it's pretty much off. It's typically the same voltage throughout the system. On some vehicles, they actually have pulse width modulation. And as we're going to see later with the Ford, goes up and down. We've seen that actually in the video a little bit ago on the other anomaly. It goes up and down across 200 and some volts down to about 10 volts. So I'm going to pull this out carefully and not losing it. Since I'm not using an official insulated tool, I'm being even more careful. My gloves protect me, but if I had a big old tool that ran across and I had a high voltage circuit that came in contact with the tool and then the tool with me, now I am connected to the high voltage circuit physically through another part of my body besides my hand. So I want to make sure I don't do that. And if there's any doubt, make sure you've got some high voltage insulated tools in your collection. You don't need a lot of them. Obviously, you're never going to use a high voltage insulation tool, even on a dead circuit, to be able to access these tiny little terminals right here, or I should say, I think they're 8mm screw heads for some of these fuses and so forth. It might even be difficult to get insulated sockets into here. So that's all the more reason you're going to be working with regular steel tools from your collection, and you want to make sure you do the correct power down and the live, dead live verification that you did do a power down. So I'm going to keep the gloves on because I've not done a live, dead live, but what I'm going to do is I'm going to check a low voltage circuit. So I'm going to get my meter back into camera action here. I'm going to be very careful to probe the terminal, and I'm still wearing the gloves, so you guys are getting the gist of it. When I tell you I wear them, even though it can be a pain. That's just this discipline you have to have. So even though I am measuring a low voltage circuit, we're going to see how low it is actually. I'm in a high voltage area, even though I do not have a ready light, and I could do a live, dead live test, and I could absolutely determine beyond a shadow of a doubt that I have no high voltage. I still have 12 volts. I got a dash on. I've got the key on engine stopped. So I couldn't do a proper power down with the key on. But what I want to show you is this particular circuit is just two wires that come to a shorting bar. That's the shorting bar right there we talked about on that cover. It's removed. I'm going to see open circuit wise what that voltage would be. So as I probe in here, very, very delicately, I see 12 volts. So I have 12 volts. In fact, I've got my polarities reversed, no big deal. I can just switch them. And not going to have any arcing at 12 volts. This is a low voltage circuit, but it's a H-fill, high voltage interlock circuit. So when that 11.9 right now, this battery actually could use a charge, the 12-volt auxiliary battery. When that computer sees 12 volts, it says this cover's off. And it sets a P0, A0, D, or some other similar code for high voltage interlock circuit, high basically. Think of it like an intake air temp sensor, and you changed out somebody's air filter, and it required you to unplug that sensor, the air temp sensor, to do the job, and you forgot to hook it back up. Well, as soon as you start the engine, it's going to set a code. It's going to tell you intake air temp sensor voltage high. It's 5 volts instead of 2 or 1, depending on what the thermistor in the intake air temperature sensor was going to do the voltage drop of that 5-volt bus or 5-volt reference circuit. So in this case, it's very similar. It's 12 volts on this particular connection, power to one terminal, ground to the other, and when this cover with the white interlock shorting bar is installed, that voltage then drops to 0. That's how it's supposed to work. If you saw voltage and then you go, well, how can we short something out under here? It's low voltage. It's an anomaly. It's supposed to work that way. Now we're going to look at some more advanced versions of this. Hopefully you're not getting bored and you've seen this before. Let's look at some advanced versions of it in some other vehicles. All right, well, look familiar? Well, that's that little white snapped onto the back of the little cover for the top of an inverter. So we were just looking at, we were measuring the female terminals that shorting bar would snap into, and basically let the computer know, hey, the cover is on that inverter, so basically like the safety is on, all right? So this is I think this is possibly a Ford, and these are the positive high voltage and negative high voltage main battery connections from the battery pack up to the inverter on a Ford, like a Ford Escape hybrid. And look below it. If you unplug that connector, then there are a pair of terminals here, shorting bars. On the other end, what this plugs into would be the high voltage interlock circuit wires, all right? Or actually the shorting bars might be on the other side, and behind there, where my hand is, might be where the wires would go, and they would follow the orange cables. Here's another example. This is a smaller service disconnect or grip plug for some of the different generations of Toyota hybrid systems, and there's a close-up of that shorting bar. So what are we looking at? We're looking at the schematic right here. So there is a 12-volt circuit with a current limiting pull-up resistor, and then a capacitor for noise and some other things. So we're going to actually monitor the status of the voltage of this wire, where my mouse is, to see is the shorting bar, is the cover, or whatever we're talking about in place. Because if it's not, then the voltage jumps from 0 to 12, and the vehicle says, well, the computer goes, nope, we can't have that. That's an unsafe type of situation. Now let's get a little bit more graphic this is actually from Weber State University. This is my colleague, Professor John Kelly. That's his hand, or a student's hand. They're pulling the service plug, and so you see a close-up of the whole procedure, and there's that shorting bar. All right, so we've done this many times on the AVI set. So there's just low voltage going to the back of that connector, and we also then have the high voltage, which is Watchdog. So here's again, this is on I think a Prius C. Another version of it, I'm back probing the high voltage, the H-fill circuit unplugged. So it's unplugged from that shorting bar that would be in place if this vehicle was intact and ready to go, and it's saying 12.6. And the same thing here. So it's just showing you where that is, okay? These are going to connect the big orange cables together, so we have a complete batch of modules, all comprising a 200 and some volt battery pack. But then we have a low voltage circuit, the Watchdog, the HVIL. Well, they'll call it a high voltage interlock circuit. And they'll say voltage high with the typical code description, which throws you off, a bit of an anomaly. It's like I'm looking for a high voltage issue. It's actually a low voltage issue. And there it is in action there again. All right, so let's move on to the update now. And there's where it gets a little different. So this was a Pacifica, this is a Stellantis product. It was a Chrysler Pacifica plug-in hybrid, and clearly tells you what to do on the label on a very large service plug. So this thing is as big as a softball almost, and it's got the huge, we're looking at 350 amp fuse And there's the huge contacts that the shorting bars, I should say, through a 350 amp fuse. This is to plug into the battery pack, the top of it, like in the floorboard of the vehicle. I have an HVIL shorting bar here and an HVIL shorting bar here. Two of them on the same thing. Let me show you what makes them tick. So here we see on the left, I'm probing with that proper test terminals actually into the connector, and I'm seeing the voltage side. The other side would just be a ground, and when we plug in the service plug, it connects it. It connects the ground, the low voltage, to the voltage that's the HVIL circuit, and this one's 9 volts. And I think it's live with the ignition on only. And then over to the right, I put another meter connection, same way of connecting, but to the other HVIL shorting bar connection. So when I plug in the service plug, I basically short those 2 wires together and it goes to 0. This one is hot all the time. It's got 7.28 volts with the key on or off. And so where that makes a difference is if you have a service plug with labels on it especially, make sure you RTFI. Take it from me, I've got a case study that kind of exposes my own stupidity. I didn't read that little cartoon. Make sure you turn the vehicle off and disconnect the 12 volt low voltage auxiliary battery system as Stellantis instructs you to do. Read the service manual, that's the RTFI, right? Read the frustrating information, find information, whatever. And then you 1, 2, 3, and 4 to get the plug out of the connector. So if you do that in the proper order, just like the factory tells you to, you won't set any codes most likely, and this is another issue. But if you skip a step or do something out of the ordinary, you're going to maybe possibly set some codes. You may not be able to clear them with your aftermarket scan tool. You may have to get the factory scan tool. And sometimes the factory scan tool's got issues. I ran into that in my case study. So let's move on to the whole concept of the HVILs and what is not allowed to close if you have an open circuit. You have a high voltage interlock circuit telling the computer, we've got something unhooked. We've got something uncovered. We've got access to something that's not safe. We don't need high voltage right now. We don't want high voltage anywhere. Keep it in the battery pack. Keep the rattlesnake box to itself and don't take the lid off, using that analogy. Okay, so here's a scenario. What if I had a 12 volt battery and it had a very intermittent, weirder things happen. So a very much another anomaly, a 12 volt battery with an intermittent shorted cell. The voltage would drop and it'd be fine. Then it'd drop and be fine. That actually can happen with a hysteresis, that it makes a relay chatter. There has been known cases where a faulty battery, 12 volt battery, that operates a relay, and there's a close-up of a relay, makes that relay turn off and on so much, it's not designed to do that much frequency of off and on and high current, and it burns up the contacts. Now, contact can burn up in 2 different types of situations. They can burn up and have a big voltage drop, or basically an open circuit. They don't want to come together, or they can stick together, like weld together, and they never let go. In this case, you got a stuck-on relay. Could that also happen with the high voltage relays called the system main relays, or contactors, as they're sometimes referred to on some high voltage situations? Most certainly it can happen. So it's not just a theory, it's an anomaly that has been proven. So for that reason, we want to make fewer sparks, the potential for like pulling the service plug, maybe while the key's on. We've all done dumb stuff, all right? Me included. So if you were to not follow the orders and you were to remove a service plug on a vehicle that's powered up, it would shut down. But you might get some arcing across those contactors, those relays. So for that reason, because those contactors, especially as cars have more voltage and more current in the higher use situations like PHEVs and BEVs especially, battery electric vehicles like this Mach-E, they have gotten rid of the high voltage system disconnect, the grip plug. There's no more orange plug. What there is, there's a little green plug, and it's low voltage, and it works on the same idea as the HVIL, high voltage interlock connection. So watch it in action, and what we're going to do, once we get this extended, we can put a padlock in here or a lockout tag where a technician can put information on there that who locked it out at what time and so forth, so we have documentation and no way you can shove that back together. Now that's purple because that's just what Ford does in their factory diagram, but here's actual hands of one of my instructor buddies doing it while I videoed it. So we release a connector positive assurance. The same thing is true on the Lightning, the F-150 Lightning. This is a Ford Mustang Mach-E. So you could use a screwdriver, you could use a padlock, you could use preferably a lockout tag with a Ziploc big enough to fill this hole you see right here, where the screwdriver's filling it, and keep it from coming back together, because it does never come apart. It just extends. You want to keep it in that extended mode. So what we're actually looking at here, we look at a schematic. There's a couple different versions of it. This is one that is part of a normal orange plug. So there's a 125 amp fuse here, and it's from GM. So I'm assuming this might be like a GM2 mode, which is a full hybrid with a big orange plug. Looks just like a Prius service plug, different part number, but it looks very similar. And it's got a big fuse in it, but look, there's a resistance that we're going to drop across this circuit in the hybrid control unit, thanks to the overall assembly when we snap it in and then we compress it like I showed you in video and I showed you live with my hands on this Prius. It's very similar. So Toyota would be very similar. The big contacts, the big fuse, and then the small shorting bar. This one using a resistance to do a voltage divider type circuit. So we have a certain voltage, not necessarily zero, that tells that computer, yep, not only do I see high voltage connected across the big fuse from the battery packs sections, and in fact, battery section 1 and 2, that still could be a 2 mode. But also, I have closed the final part, the HVIL section of that service disconnect. So on this GM vehicle, having a section 1 and 2 is not necessarily meaning you've got like a Chevy Volt. It could easily be a prismatic style modular battery pack, like similar to the Prius behind me, and you basically break the battery into 2 sections when you remove this plug. But we still have the HVIL. In this case, not a shorting bar, a 39 ohm resistor. Kind of interesting little anomaly as well. So look in the Stellantis manual here. Whatever model this is, and I pulled this out for a reason, it probably is a Pacifica. It could be a Jeep. But here is a bunch of low voltage circuits, okay? So let's follow them. So we have a module slash power inverter. Sounds familiar, right? An inverter. And here is an electric motor. Now it's very unlikely you're going to have high voltage that you're going to have disconnecting between the module and the inverter, or the inverter and the motor. Motors have 3 big orange cables going to them. So this is not the high voltage circuit. This is the interlock circuit. So we have a pair of wires in a circuit here at the power inverter, the inverter, and they also, this loop, this HVIL loop basically, kind of like a CAN bus when we loop things around in different modules. Here is the electric motor, so if the electric motor gets unplugged, we know it. Inverter gets unplugged, we know it. Motor gets unplugged, we know it. A high voltage test port. That's interesting. And now we have a high voltage disconnect. So this would be like could be high voltage, but look, it's also going over here, again, 2 wires, 2 wires, 2 wires, a battery pack control module. So this is calling it up here a high voltage interlock safety loop. So this is HVIL. So this is not, as we think of, the big orange cables. This is what gets disconnected when you pull something apart and reports into the module, in this case, the battery pack control module, that something has been disconnected. That's what HVIL's about, all right? Let's move on to our next illustration, and this is a Jeep, another Stellantis product. This is the Jeep 4xe, so it's a plug-in hybrid, about 340 or 50 volts, or 360 volts, somewhere in that range. And we're going to run around with just the engine off if you want to. If you have a fully charged large battery pack, that battery pack is behind the front seats, underneath the little bench bucket seats that are in the back of the vehicle. So you flip the seat cushions forward and you get the access that we're seeing right here. And you follow the instructions in a de-energize type of a procedure, power down. And it tells you in the manual, these are not uninsulated gloves, by the way. These are the shells covering a set of high voltage gloves. And the technician is using the leads from the meter to probe into some test ports. So these test ports are 4 millimeter. They don't tell you that in the manual. They're 4 millimeter. They're designed for the lantern tips that a lot of meter tips have. So that's what the technician's doing to make sure that high voltage went away. When you do away with an orange service disconnect plug and you use a low voltage HVIL-like circuit to depower the vehicle, or a scan tool, or both, you definitely want to make sure you have your ducks in a row when it comes to what's called the live dead live test that most manufacturers are now moving towards when you have this type of arrangement. And that's what we're seeing right here. We're seeing the dead of the actual test ports on the battery pack. And then if you had used a battery proving unit, a high voltage proving unit like the Fluke PRV 240, or you use a wall socket or a 12 volt battery, whatever you want to use, make sure your meter is connected correctly and you're not having a bad day of, reading your meter, because you want to do the live. Hey, I got a circuit, the dead, this is dead right here, and then back to live again. And that's what we did here. But what's the anomaly is when you pull that cover off, it's one more HVIL. So we have 2 dowel pins that kind of remind me of a dowel pin, but they're welded, spot welded metal pins, different lengths, and you remove the tamper-proof torque screws to pull this cover off. These pins are engaging some circuits in here, not live electrical circuits, but switch circuits. These are more cases that might say trip switches. And let's take a look at the schematic to see what we're talking about. I'm going to blow this up nice and big. So this is what the area you were just looking at. This is called the high voltage test and service module. And you see a high voltage negative and a high voltage positive. Those are the 4 millimeter lantern jacks, just like the front of your Fluke meter. Don't even think about using those banana plugs, those simple little jumpers that you get that have 4 millimeter lantern jacks. You want to use official 1000 volt category 3 meter leads and 4 millimeter lantern tips on the end of your leads. But these are current limited test ports, and that's what these big resistors are for. So they kind of keep you. Yeah, you can see high voltage if for some reason the contactors, the relays, didn't come undone. So here they are, your main relays, a pre-charge, a contactor main positive, and a negative, just like we seen the Toyotas earlier. That works the same way. All right, so the test cover comes off. What were the interlock circuits? What were the HVIL? These blue wires here. Now, I'm not sure how I could measure that on this particular vehicle, but you could, if you could figure out where the connections are, see the HVIL circuits, and they come from the battery pack control module, and they are pulse width modulated. So if you remembered seeing some of this Ford Fusion I talked about, where the voltage ramped up and ramped down, manufacturers do their HVIL circuits differently. They do their high voltage leak detection circuits differently. So this is HVIL, it's pulse width modulated. We've seen on the Stellantis, on the Pacifica plug-in, we saw, what we see, 7 volts on one HVIL shorting bar circuit. We saw like 5 volts on the other. So it varies. That's the anomaly to learn. There's no set standard for how these watchdog circuits work, but they do work, and we need to know what normal is as far as anomaly goes and what's a concern. So that's a little peek into the battery pack of a Jeep 4xe or any plug-in hybrid for that matter from Stellantis using this particular technology. Now going forward, a little bit of humor here. So because relays, including high voltage contactors or system main relays, can go bad, it's rare, but they can. The more current and the more life and years and the more times they're off and on, the more potential there are for arcing issues. People that are enthusiasts of any brand of car, I'm not picking on Ford or anybody, but I'll say that when you have an owner's forum for a really cool car, you know, what Tesla or a Mach-E or whatever it is, people will dig in and they'll find answers from their dealerships. And What happens when the relays don't go open and they don't shut, they don't go open? Another list of things we have to be concerned with. And I think it's funny that, we have a little owners forum, and they're into it and they take a good sense of humor. So stop safely now if that HVB-JB, high voltage battery junction box, doesn't work properly. And to fix the problem, to give Ford all the credit where credit's due, they came out with a solution. Actually, it was they went ahead and did the full National Highway Traffic Safety Administration recall, where owners of certain VINs of Mustang Mach-E's, and I'm not sure if it extended to the Lightning pickup trucks or not, but maybe at some point some of those things may, but their onboard charging modules. They did actually the SOB, the Secondary Onboard Diagnostic Module C, and that is a battery energy control module, I believe, and the Secondary Onboard Diagnostic Control Module. I think that might be the battery charger. When you plug into a level 1 or level 2 charger, that module that charges, it's basically an inverter, jumps the 240 or the 120 of AC up to 300, almost 400 volts of DC. That module and the battery, they call it the Battery Energy Control Module, the BECM, those modules were reflashed with software updates, and it made the potential for this problem with contactors be reduced to like 0 to none chances. But in the meantime, in case the problem ever were to reoccur, part of that software update, check this out, look at the DIC, the Driver Information Center, that laptop on its side that the cool Mach-E has, or a lot of cars, even Teslas and Lightnings have these. But look at, they added a new little control with the software update that says unstick contactor. How can you unstick a contactor by pressing a touch screen on your Mach-E? It's simple. The battery control module, whatever is going to control the relays, the system main relays, it can vibrate. It can send a message, a buzz effect, and that oftentimes can take, with 12 volt control, can take a high voltage contactor and make it start to jump loose and start working again. So it's kind of a backup to the backup. Very ingenious, but if you didn't know that, if you didn't know there was a software update, and you didn't know what was here to address the anomaly of occasional sticking shut or open contactors, you wouldn't be able to get that car moving. So to not be outdone with the low voltage ways of powering down the vehicles, oftentimes a combination or an option, you can use the factory scan tool, or if you have an aftermarket scan tool that can communicate with the battery electronic control module, and ask it to prohibit the closure of the contactors. That's the equivalent of a power down procedure. Again, drill down on your live testing to verify that you have indeed depowered or de-energized the vehicle, because you're relying on little connectors again. So there's a picture of it blown up. There's the BMW. So the same thing as in an X5 PHEV. This is a little i3 total electric vehicle. So they are using these in BMW, and you have to make sure you know how to follow the RTFI, read the fine information in order to make sure, like in the X3, that's a big SUV, plug-in hybrid. It's got two 12-volt batteries and a big lithium-ion high-voltage battery. So disconnecting those 12-volt auxiliary batteries in the correct order, before you do this, read the directions or you set the codes that oftentimes are hard to get out of, and you made things worse than what you found it. Well, that was just a couple of anomalies that can occur on electrified vehicles. We talked about HVIL, and we talked about high voltage leak detection or the high voltage isolation circuits. Whichever you have on your vehicle, make sure you check other known good vehicles, and as always, follow all the OEM safety requirements. Especially just keep that acronym in mind, RTFI. Read the frustrating information. It'll pay off for you in the long run, both with safety and effectiveness. On behalf of Delphi and Automotive Video Innovations, AVI, thanks for watching. Stay safe and God bless.